Hello, my name is Alan Leonard. I'm going through my Comp 4320 Introduction to Networks Assignment 6 now. For number 1, we have to explain key characteristics of SDN. Go through different parts of that. It uses multiple layers separating the control and data planes from each other to effectively send data and change parameters across them, with one layer being the switches and the other one being the controller. Control plane sets these parameters, is connected to the application layer directly, and has instructions change, while data plane is where all the everything across all the switches is connected through to the different networks. The controller has access to the control plane and creates sets and changes the flow tables used across the data plane, affecting which is switching directly using OpenFlow to connect to these networks. Number 2, describe the role of link layer and so on. Link layer is one of the more complicated layers, as it helps translate, encodes, and decodes information across it from senders to receivers directly. Error detection comes in multiple forms. Parity, with using a code that is checked for changes to determine if there is errors across it. It has one specific code, and when they're sent across it changed, finds that an error has occurred. Checksums are use simple algorithms during transmissions, but can't help if an error occurs and is not built with great security for tracking being attacked. And CRC uses complex and very effective ways of of error detecting, and I'm sorry, the last word was on my notes. It's very effective, but it also takes a lot more resources to work accurately and efficiently across everything because of how much more complex it is. CRC would be the best for the scenario we were given, as we were asked for an optimal for error detection mechanisms that constantly suffers from frequent packet errors. And CRC would be the best for just stopping and not having to retransmit as much. Number 3, explain how SDN can improve network resilience. SDN is used to allow networks to work more effectively and manage much more efficiently across all of the huge amounts of networks. Helps reroute packets easily, switching paths across different networks if needed, to stop huge amounts of congestion and high traffic from occurring. How can it interact with link layer mechanisms and dynamically adjust to all of that? SDN has easy access to link layer through the OpenFlow and can adjust flow schemes, change paths, and everything else much more easier because of this, as it directs the top layer above the switches and everything, and just easily connects through them. In the scenario that we were given, SDN would use OpenFlow to find the high traffic networks and switch some paths around so things get to go around each other without fully interacting and colliding across them. Lower transmission rates if it was needed, and detect any errors across those links using the different link layers. And also try to prioritize different links across the network, much less resource allocation needed. So they get done quicker and easier, and then those resources be used for others. Number 2, 3 categories of multiple access protocols that were given is channel partitioning, random access, and taking turns protocol. Channel partitioning divvies up the resources across different channels, separating them all up and letting them take turns across that, using equal bandwidth across it and time. Turn taking allows each one to go one by one, using all the resources, taking turns essentially, and making them go through as quickly as possible, while random access sets them all at different random times and uses multiple other smaller parts or subparts in it in order to avoid collisions. And if a collision happens, since it doesn't receive an acknowledgement, they never stop trying to send them, so they'll just go back in the list until another random time in the given time frame. For the solid Aloha, CSMA, and CMSA with CD, the difference is Aloha uses connections to send whatever, but will keep resending at random times until it receives that acknowledgement. CSMA is similar, but it waits for the connection to be idle before sending to prevent a collision, so that way there's not as many resubmissions or retransmissions needed. And CD is the best across those because it also has the ability to detect if a collision will occur, so it just terminates and stops it from even happening. or from even sending, and then will eventually be sent another time. This completely stops collisions from happening. It allows the key effectively being used across the bandwidths and everything. For the scenario given, because how it says specifically host needs to send packet to another host in a different subnet. No, I'm sorry. Here's a scenario where wireless networks experience high collisions. CSMA CD would be the best for this to just completely prevent collisions from happening altogether, or at least for the most part, and would actively detect and prevent them from happening as was transmitting. Now, number 2, explain the role of MAC addresses and LAN communication, etc. MAC connections addresses are specific to each device and computer, and IPs are across the same network and are used globally instead of just primarily for individual computers. IP addresses are mainly used for networks and routers connecting across on this global scale and used for security across these large-scale systems, while MAC addresses are individual and can't change as easily as IPs can across these different networks when it's swapping over to different networks. They easily adapt you to the other ones using IP version 4 and version 6. ARP works by checking if the receiver in the network's cache of addresses, basically the computer connects up to the router, network, whatever it's connected to, sees its whole list, and if it's connected, it just immediately goes to it. If that doesn't, it goes up to the next router and looks for it from their list, and so on and so forth. And from the given example, if it needs to send to a different subnet, it would first go up to router A, look through all the MAC addresses, wouldn't find it, would go up to router B where the actual one is, because it would be searching through their IPs and find that they have it, and then go through there. Be routed straight to that. And 3, explain how Ethernet switches using MAC addresses, learning and everything. Ethernet connections actively have multiple layers of communication. Using this allows it to maintain its MAC address and connect over on other layers to their flow tables and quickly transport over where it needs to go as quickly and hopping around without causing any collisions or traffic needed. Traditional hubs allow a large amount of bandwidth to be shared and is much more larger distance availability because of this, and because it doesn't need the wires and everything. But Ethernet combats a lot of this by being more efficient, faster, better for individuals on a huge, larger scale, because now not everything is shared. It's all personal, like bandwidth-wise. And also, it's much faster. The only problem with Ethernet being that it's much more resource heavy, and how the fact that we have to have these cables per every single device. And it's much worse compatibility with across that, because we're having to switch over into things that don't use Ethernet. In the scenario given, Ethernet connections would use the self-learning to view traffic, hop on across different layers to avoid these collisions, and dropping frames to create bridges would help frame filtering and stop these loops from occurring in the first place. Problem 3, I wrote off everything I needed for this one with on that 1, 2, with that first message would be sent at 1, next 3 would be sent at 2, next 2 would be sent at 3, next 3 would be sent at 4, and last 2 would be sent at 5, because of the nodes that were sent in. Now, the only one that would actually be received is the first message, because all the rest would be sent at the same time as others. And for B, much different math for this one, because it was using a 0.4 system, or time units across them. 1 would be sent, 2, since it's more than 0.4 away, would be sent, 3 and 4 that were in that time range for number 2, so that both of those would not be sent. 5 would be sent, 6 is too close, so it would not. 7 would be sent, 8 and 9, both in that time range, 9 just barely, so 8 and 9 would not be sent. 10 would be the last one sent, with 11 being way too close as well. So that would be 1, 2, 5, 7, and 10 that all get sent. And none of the messages had any collisions, as 3, 4, 6, 8, 9, and 11 were not sent because of the errors that were detected. Alright, thank you.